Okay, guys, I miss seeing you today, that's for sure, but we're going to make the best of it. So, as usual, we should start by accessing our 7.3, 7.4 homework. I'm still expecting you guys to correct your work, show corrections, and ask any questions about it. So what I'm going to do is I'm just going to scroll through these real quick. You should pause at each question because I'm not going to spend video time explaining or anything. So just pause it. It's going to go quick. Okay. And then we'll move on to our lesson 7.5. All right. So make sure you guys are, get in contact with me with any questions, right? Email or Teams chat. That's always it's a good one to use. Okay. So we're going to talk about quadratic equations, right? It's all about quadratics, but we're going to focus a little bit more on asking ourselves and recognizing how many solutions certain quadratics have. So we're going to investigate some quadratic equations and parabolas to see what's the difference between having two solutions, one solution, or no solutions. Okay, so for a warm-up here, if you guys want to take a minute, hit the pause button, think about these four statements. So we're going to decide whether they're true or false. So, pretty easy task. First one says 3 is the only solution to x squared minus 9 equals 0. So if we have x squared minus 9 equals 0, then we know that x squared must be 9, since we can all agree that 9 minus 9 would give us 0. So then the question is, well, what value squared, right? What value squared gives us 9? It's the question we're asking. So we know that 3 squared gives us 9, but also we know from last class, and we're trying to bring that idea back, is that we also know negative 3 squared equals 9. So this is false because we know that x could equal 3 and x equals negative 3. All right, second one, a solution to x squared plus 25 equals 0 is negative 5. Well, if things are solutions, that means they will make the equation true. So let's just test it. Negative 5 squared plus 25, does it equal 0? Negative 5 squared, negative 5 times negative 5, we know is positive 25, plus positive 25, does that equal 0? Absolutely not. It equals 50. So we know this one's false. Third one says x times x minus 7 equals 0 has two solutions. Absolutely it does, right? We know, hopefully, right, we recognize this, that we've seen, look, we have two different values here. In one case, the x piece is 0, which means we'll just make it 0. And in the other case, the x minus 7 piece is 0. Well, what x value would make the x minus 7 piece 0? Well, 7 minus 7 would make it 0. So, of course, we have our two solutions. And then the last one is asking whether or not 5 and negative 7 are solutions. Once again, how do we know if they're solutions? We test them. So let's try 5. 5, plug in 5 for x. Does this equal 12? 5 minus 5 is 0. 0 times 12? Definitely not 12, right? Because we know 0 times anything is going to be 0. And the same thing would happen for negative 7, because for negative 7, it would make that value 0. So this is false. Now, what would be true, right? What would be true is if this equation were equal to 0. Then we would want to find the values that make each binomial 0. But it's different. When it's not 0, it's a different case. And when it's 12, these will not be the solutions we're looking for. Okay, let's move. We're going to be utilizing Desmos today. Whether you want to utilize it, whether you just want to watch me utilize it, either way, we need to be able to make sense of what we're looking at. So we have three equations here, and our boy Han is going to solve them all by graphing. So they're very, very similar. As you notice, the only difference is we have a different value on the right side of our equal sign. Excuse me. So to solve the first equation, Han graphed and he looked for the x-intercepts. So let's go to the graph. And we're going to look for the x-intercepts. So we got our graph here. Let me change this actually. Let me change it to a different color. Blue is a little more favorable. Take a picture here. Dump it into OneNote. Shrink it down a little bit. Okay. So he's looking for the x-intercepts, which we see that it crosses the graph here at x equals 3. Actually, you know what? Let's write coordinates at 3, 0 and at 5, 0. And the thing that we want to ask ourselves is, why can the x-intercepts be used to solve this equation? Well, guys, we know that because we know that the values that make this 0 and make this 0, when we multiply together, will ultimately give us a result of 0. So the x-intercepts can be used because the x-intercepts tell us the x values when the graph is at 0. Okay? So that's the whole reason that the x-intercepts are helpful in this situation. They tell us when the graph has a y value of 0. And what are the solutions? Well, of course, 3, 0 and 5, 0. We can look at it on the graph, or we know our method for solving our 4 x-intercepts. Okay, now, number 2 says that San halved. That's not right. Han solved this next equation. So the second one here, he solved it and wrote x minus 5 times x minus 3 plus 1 equals 0. And right, real quick, here was the original. And all Han did was said, you know what? I don't like that -1 over there. So I'm just going to use some equations balancing skills. I'm going to cancel that out. And I have to put the +1 on the outside because it doesn't break into the parentheses. It has to stay on the outside. So then he graphed this equation. Han likes getting things equal to 0. And hopefully we're picking up and starting to recognize that 0 is really helpful. And we'll see why that is. So let's go back to Desmos and we're going to plop a +1. And let's see what changes here. Well, hopefully, what we noticed was now, look at where the graph was. It kind of dipped down below the x-axis here. And now the graph has been shifted up. That should make sense, hopefully. The graph has been shifted up due to that +1 on the outside of the equation. We know that adding numbers on the outside shifts our graph up or down. So now we look and see, and it says use the graph to solve the equation. Well, guess what, guys? We're asking ourselves, when is the parabola equal to 0? Which means, when is the parabola touching the x-axis? Where are the x-intercepts? And in this case, we have one solution at 4, 0, because it was shifted up a little bit. Here we had 2. Here we had 1. So it says solve the third equation using Han's strategy. Okay, so our third equation was x minus 5 times x minus 3 equals -4. So x minus 5 times x minus 3 equals -4. So Han's strategy, we're going to get that to be 0. So we're going to end up with x minus 5, x minus 3 with a +4 on the outside equals 0. So let's go to the graph. Let's go to Desmos. Now, if we know that right now with a +1, the graph is just sitting on the x-axis and it's touching it once, then we should expect that if we add a +4, right, here's our original, if we shift the graph up to a +4, it should sit somewhere up here. And sure enough, it was shifted up even higher. So, what can you say about the solutions? What can you say? Because remember, guys, when stuff is equal to 0, it means we are looking for the x-intercepts. We are looking for x-intercepts when we have our equation set equal to 0, because that's the 0 line. So there are no solutions. It doesn't touch, right? It does not touch the x-axis down here. So there are no x-intercepts that make this true. So 4 says, why might it be helpful to rearrange to get 0 on one side? Because if we set the equation equal to 0, that means we are looking for x values that are x-intercepts. Because that's what we do, like when we're looking for when does it equal 0, it means when does it cross the y value of 0. Then from the graph, right? From the graph, it's easy to see if and where the graph crosses the x-axis. So really, we're just setting ourselves up to look and see, oh, are there any x-intercepts? So how many solutions does each of the three equations have? Well, we had 2 for the first, right? 1 for the second, and none for the third. So that's all we're asking ourselves is, right? Let me put it this way. So here, I'll come back down here. So this is like, this Are You Ready for More is such a great example of how you can, like, you don't necessarily have to manipulate the equations, but how you are going to, you know, see like how this graph looks. Okay, so here, just think about this. I'm gonna keep this simple. Is all I want you guys to do is think about this. So y equals x minus 3 times x minus 5. We know that this represents a quadratic, which in this case, you know, we know the graph will be a parabola. And then you look at the y equals -1. Okay, this is the one that we just did. This just represents a horizontal line. Okay, just stick with me here. We're not going to go crazy on this. So since they're both equal to y, it means we can set them equal to each other. So x minus 3 times x minus 5 equals -1. And guys, it's a very simple question that we are asking ourselves, because this represents a parabola and this represents a line. And the question we are asking ourselves is, what x values make the parabola equal to the line? I mean, that's exactly what we're saying. If we were to talk this equation out verbally, we are saying what x values make the parabola equal to the line. So if we go back to this example here, and we'll do here, I'll just make it look the same, x minus 3, x minus 5. And then we go and graph the line, y equals -1. Look, they intersect. So they have some sort of overlap, and that value is 4. So all you're asking yourself is, where does the parabola and the line, where are they equal? So for example, if I made the line y equals 3, look, it crosses at 2 places, at 2 and at 6. So that's where the two things are equal. Or if I make it like -2, look, they don't cross because the parabola is going to go up and up forever and the line stays constant. So you can either utilize Han's strategy by moving things over and always getting it equal to 0, right? And wanting to get it equal to 0 here. Or you can graph the two things separately and say, well, it's an equation. So that means where does the parabola equal this line? If they cross, sometimes they'll cross in 2 spots. Sometimes they'll only touch in 1 spot. Sometimes they won't touch at all. Okay, so let's move on to kind of the bottom of page 4 here. So you guys you can graph all of these, right? So you know what? I know that we can think these through. Like I know that we can think of the numbers that squared equal 121. I know that we can determine that that's 11 and negative 11. But if we graph it and if there comes a time where we're not quite sure, we can then utilize graphing to just help us see the picture. But these are pretty straightforward for us. So we're asking ourselves, right, what value squared is 121? So we know that x could be 11 and also negative 11. Okay, certainly for the next one, we're thinking, well, what value minus 31 would give us 5? Well, we know that x squared needs to be 36 because 36 minus 31 gives us 5. So we're like, okay, so if x squared is 36, then what's x? Well, we know x could be 6, and x could also be negative 6. Okay, now we come across something where it's like finding our x-intercepts. Look, it's the ZPP, it's zero product property. One value, some g, times some h gives us 0. Well, we know that g could be 0, or we know that h could be 0. Well, it turns out that it's the same binomial repeated. So if we want to make this 0, x needs to be 4. If we want to make this 0, x also needs to be 4. So it actually turns out where this just has one solution, where x is 4, because it just so happens that the factor repeats. And sometimes that happens, right? We've seen that as an example. All right, so now we get into these three. And this is where it gets this is where we can't use ZPP. Why not? Because it's not equal to 0. That's the z in 0. This is not 0. So that's the whole thing, zero product property. Now, we could probably think this one out, but we might as well use graphing as a strategy. So here's what I'm going to do, because I don't like to have to try to manipulate stuff. I just want to keep it as it is. So I'm going to graph the parabola, which is x plus 3, x minus 1, and I'm going to graph the line, which is 5. And I'm going to see, do they intersect? Are there x values that make both of them true? Are there x values that make both true at the same time? Because that's what it needs to be an equation. The x values need to make the parabola true, and it needs to fall into line 5. So x plus 3, x minus 1. So we're going to do y equals x plus 3, x minus 1. So we have a parabola here that we were expecting. And now we're just going to see, does it intersect and cross with the line 5? Look at that. It does. So there are 2 points at which both of these will simultaneously be true. And with Desmos, we can hover over it. So it's at when x is negative 4 and when x is positive 2. So I'm just going to snip here. Let me get the right values in here so we can see it. Yeah, that's good enough. So there's a point at which both things are simultaneously true. So I'll throw that over here. So we can see that So x equals -4 and x equals +2. We have two solutions. Okay, now let's go to number 5 here. We're asking ourselves, here's the parabola over here. We know it because it has an x and a squared, and here's a line. So we ask ourselves, what values of x will make the parabola and the line true at the same time? So let's go to Desmos. X plus 1 quantity squared, and the line, what do we got? -4. Y equals -4. So sure enough, right, just knowing that this parabola is going to sit where it sits, right, there is no interaction. There's no intersection. There are no x values that will make these two things true at the same time. In which case, right, it's pretty easy to see that there's no intersection between these two. So there are no solutions. And then finally, we could do the same thing with x minus 4, x minus 1. So let's do y equals x minus 4, x minus 1. And we're trying to see when will that equal 990. Now, sure enough, we got to zoom out quite a bit. But if we go in and zoom in here, we see that it crosses twice. The line and the parabola intersect at -29 and +34. So we have two solutions. So x equals -29 and x equals 34. Now, even if you were able to kind of think through number 4 in your head and come up with -4 and 2, there's probably not a good chance you were able to do that with 6, which is why the graphing is a successful strategy. So we want to make sure that we can use that as one of our strategies. Okay, so we're going to analyze something that Priya did here. It says she's looking at x minus 5 times x plus 1 equals 7. Priya reasons that if this is true, then either x minus 5 equals 7 or x plus 1 equals 7. So the solutions are 12 and 6. Okay, well, here's the thing though, guys, right? Let's just test out the solution to be 12. Like, that's fine, except for the fact that if we test out 12, 12 minus 5, 12 plus 1. This is great. It gives us 7. The only problem is that this gives us 13, right? Priya was using the reasoning to think that, well, if 1 is 7, then the other thing needs to be 1. But we were adding 12 in for x. So 7 times 13 is definitely not going to be 7. And the same thing is going to happen for 6. So Priya was probably thinking, again, she was kind of treating it as ZPP, but this is not a case of ZPP because it's not equal to 0. All right, so then number 2, consider x squared minus 10x equals 0. Diego says to solve, we can just divide each side by x to get x minus 10 equals 0, so the solution is 10. Mai says, I wrote the expression on the left in factored form, which gives us two solutions. Do you agree with either strategy? So I think hopefully we should agree with Mai that when you have x squared minus 10x equals 0, you can't eliminate an x and just divide it off like Diego did. You can't just get rid of it. But what we can do is we can factor, like Mai said, we can divide both sides by x, but we're writing this in factored form because that x is still part of our solution. So we just want to rearrange it so that it's in factored form, and then we know that we can use ZPP, and we'll have two solutions, 0 and 10. So remember, when you are factoring, that 1x is still included in the original. It doesn't go away. It just changes its position, and it changes the way that the equation looks. Okay, so let's do a little synthesizing here. How would we solve this equation? We would break our factors into two pieces and set each to 0 and find x, right? So we break them where there is a break. Take this piece, set it equal to 0. Take this piece, set it equal to 0. Hopefully we can see our solutions will be x equals 0 and x equals 250. The two x values that would make each piece become 0. All right, if we choose to solve by graphing, is it necessary to rearrange and rewrite the equation? No, right? It's not. No, because we saw that you can graph the parabola on one side and then graph the line on the other. Let me draw just a reminder, just like we did here. You don't have to rearrange it. You can just graph the two things separately and see if there are interaction points or intersection points that would signify a solution. Can we use zero product property to solve? Of course not. No, because it is equal to 100. So by nature, it is not the zero product property. How would you solve this? I don't know. I would say we can graph. We can graph the parabola on one side and then graph y equals 100 and see if they intersect, meaning that there is a solution that makes both of them true. How can the graph tell us how many solutions? We look at the number of intersection points between the parabola and the line. Could be 2, could be 1, could be none. Maybe they don't interact at all. Okay, so graphing is a super useful strategy that we need to be able to utilize. And just a reminder, right? Zero product property, it has to be equal to 0. Okay, so what I want you guys to do, take a quick pause, see if you can just determine not what the solutions are, just does it have 2, does it have 1, or does it have none? So take a pause right now. You got 3 of these. See if you can think about these. Pause the video. Of course, I'm just going to go right into the solutions here. So, for example, for the first one, if we like to see things in terms of 0, that's fine. But we could just ask ourselves, what value squared gives us negative 16? Now, even if our first instinct is negative 4, we should quickly debunk that because we know that negative 4 times negative 4 is positive 16. So if you're struggling to come up with an answer, that's because there isn't one. And if we like thinking of things in terms of 0, then let's just do that. So let's balance this 16 onto this side. So we get x squared plus 16 equals 0. So once again, right, what we're looking at is to say, if this is a graph, this is a parabola that is shifted up 16 units. Will that intersect the line y equals 0? Absolutely not, right? You could just do a quick sketch of this. This parabola is going to be way up here at 16, and here's the line y equals 0. No way that's going to interact. No solutions. Either you thought it through and you knew that no value squared can give you a negative 16, or you looked at it from the graph. Now, this one, this is our bread and butter here, right? We see the two separate pieces. We have our G piece and our H piece. So in this case, we'd need x to be 0. And in this case, we'd want x plus 2 to be 0, which means the x would need to be negative 2. So here we have our two solutions. And then lastly, we break this up into our two pieces, but we notice it's the same factor. So this is the same factor, just repeat it. So we know that in order for this piece to be 0, if x minus 3 needs to be 0, then we know x needs to be 3. Okay, got a little summary here at the bottom. I appreciate you guys. We'll reconvene. We're going to be doing the same thing on Thursday. I'm going to be out again. But yeah, so we should head right to our homework. We should start 7.5. As use your class time now. It's posted in Teams. It's going to post also in OneNote. It's due next class, which is Thursday, because we have no school. You guys don't have school on Wednesday. Okay? Do your best. Appreciate you guys. We'll talk on Thursday.